as you can see today, we're going to be learning about the thermodynamic of the reactions, of chemical reactions. This is something you may have seen already in general chemistry, so it may be a pretty basic review of things that you already know, but I want to re-emphasize them. So a couple of things that I want to define here is what is an energy diagram for a chemical reaction, which is basically a graph in which we basically show the change in energy that are taking place during a chemical reaction. So in an energy diagram, we usually have it's a 2D diagram. In the y-axis, we have energy. In the x-axis, we have reaction coordinate. So basically, it's a plot in which you measure how much energy or how is the energy of the reaction evolving with as the reaction progresses. Okay. In the x-axis, as I said, we have the reaction coordinate, which is basically a measure in the change in the position of the atoms during the reaction's progression. So the energy of the reaction evolve depending on the change in the structure of the molecules, the new bonds that are being formed, the bonds that are being broken, and that's how we basically track any reaction, not only in organic chemistry, but in any chemical reaction. So here is an example of an energy diagram, okay? So we have energy here, as I said, in the y-axis, and we have reaction coordinate in the x-axis, right? And here is a plot of an energy diagram, typical plot for the reaction. So we can see here a few things that I want to emphasize. So first of all, here we have A and B, which are the starting materials. So these are the two reactants. Okay, could be, remember in chemistry we can show one molecule reacting and reagents and things like that. So all the reactants will be here. And then we see how the energy goes rising here. It reaches a high point here, and then it goes down, and it reaching a well here valley. So this is basically the typical shape of a first step in that reaction. Okay, so in this step, A and B are actually reacting, and the transformation in terms of bonds that are being broken, form new structures, is leading to this change in energy, and there is a point in which now there is a restructuring of this new reaction, new molecule, new products, forming this final product here. This is the final product of the first step of the reaction. Okay, this is the first step of the reaction, and this is the final product of the reaction of that step. So for A and B to reach this point here, obviously there need to be enough energy to surpass this amount of energy here, which is what we call the activation energy. Okay. So then once that we have the first step is finished, in the second step there is also a rearrange of structures and atoms to lead to another structure here with higher energy. Okay, and then this rearrange to something new, which, as you can see, has a lot less energy, which is C and D. Okay, so for this second step, there is a second activation energy here. Okay, so a few things about this that we have to comment is this is an overall reaction in which A and B are transformed into C and D. That's the overall reaction. A and B leading to C and D. Now, in order to A and B be transformed into C and D, there is a reaction mechanism. Okay, this is something we're gonna see a lot in organic chemistry. And this reaction mechanism implies two steps transformation of A and B into a first intermediate, and transformation of the intermediate finally into final product C and D. This reaction, you can see how A and B, they do have higher energy as compared to C and D. So can anybody tell me if this is a diagram for an exothermic or an endothermic reaction? What do you guys think? It's exothermic, that is correct, because the energy of the product is lower than the energy of the reactants. So an exothermic reaction is a reaction that is actually releasing energy into the system. So it's basically a thermodynamically allowed reaction. So remember, and I'll show you now, you should have seen in Gen Chem and heard about free Gibbs free energy. So basically it's the way of thermodynamically tell if a reaction is permitted or not. Okay, so the overall reaction here is exothermic because the final products are lower in energy as the reactants. Because it's an exothermic reaction, in general we can say that this, as I said, thermodynamically allowed. Okay, and mostly in chemistry, reactions takes place in such a way that we're forming more stable products. Okay, that's the driving force in nature for reactions. It's very difficult to have a reaction leading to something less stable unless you force it, you put energy into the system. Then it's going to be hard even to isolate that compound. Now, but the point here is that even though if you have an exothermic reaction, as I said, those reactions, those transformations will happen or can happen through different mechanisms. And these reaction mechanisms might imply one step or several steps. Okay? In this example that I'm showing you here, this is a reaction with two steps. How do you know that? Because you have one rise here, and then you lower the energy, forming an intermediate, and then a second, the same thing. Okay? So from these two steps, we have two energy of activations, one here and one here. Clearly, the energy of action of the first step is much higher. Okay, and I'm going to add something in the slide that I think I want to emphasize too here in this class. So the first step has a much higher energy of activation. Okay, so that we know, and then the second step. Therefore, the step with a higher energy of activation, we will call this the slowest step of a reaction. And I'm assuming that you guys know this, okay? So, and this is really important because basically the slowest step of a reaction is a step that will determine the reaction rate, okay? So let me repeat this idea over here because that's so important, and I want you guys to really understand this before we move to organic chemistry. Okay, so in any transformation where we have, obviously, if we have only one step, that single step will be the slowest step, right? But if we have a transformation that implies several steps, the slowest step is the one with a higher energy of activation, okay? And that's the rate determining step, meaning that the overall reaction rate, okay, will depend primarily on that first step. The second step doesn't really have a major impact on the reaction rate because it happens very fast. Okay, that makes sense. And that is going to be really important for next semester. Just remember this, okay? So overall, the summary of this is, in an energy diagram, we show the energy versus the progress of the reaction coordinates, okay? So reactions can be classified into exothermic if the products have lower energy than the reactants, or endothermic if the products have higher energy than the reactants. Any transformation can be happening in either one step, single step reaction, or there might be a reaction mechanism that includes several steps. It could be 2, 3, 4. We don't know. Depends on the case. In this specific example, showing you a reaction that actually has 2 steps. When there are multiple steps, the step with a higher energy of activation, that will be the rate determining step, or the slower step. Okay, so basically, and you will remember that, as I said, next semester, if you're looking at the overall reaction rate of a reaction, you need to focus on only one step, the slow step. So if I'm asking in a reaction, say you have a reaction that can produce 2 or 3 different products. If the question is which of the 3 products form faster, basically is the one having the lowest energy of activation in the slow step. Okay? And in the next class, I'll bring you some examples, but this is a really important idea that I want to show. I'm actually going to write this again because I think I want you guys to really so why is that important? Okay, somebody had a question. So this lower step, if after, so somebody's asking what if this lower step is after the faster step? It doesn't matter. There is only one slower step. This lower step is the one with higher energy of activation. It doesn't matter if it happens first, second, or third, or last. Okay? But that's the rate determining step because it's the one that requires more energy to be surpassed in order to form the products. Okay? So the important thing here is, so I want you guys once again to expand how you think about this. Okay? As I said, slower step, and I'm going to rewrite it over here. Slower steps, rate determining step. Okay, so obviously when you have multi-step reactions, if there is only one, that's it. And why is that important? Well, that's important because, okay, we have a reaction with potentially 3 different products. Okay, so and we'll see that in the in organic chemistry in the next semester. So if we have a reaction that potentially can lead to 3 different products, then you could ask the question of, okay, so what is the major product of the reaction? It's a pretty big question that you will face many times in OrChem next semester. Okay, so many times there are, and this basically means when I said reaction having 3 potentially different products, that basically means 3 different reaction pathways. 3 different, so you could draw 3 different energy diagrams because for each reaction there will be an energy diagram. Okay, so then if you ask a question, what is the major part of this reaction, what you have to focus on is on the slowest step of a reaction. Okay, so the answer to your question would be, and this is a way of reasoning reactions that is so important. So the answer to your question would be the major product is the one forming faster, because if it forms faster, then you will get more of that. It's just logic, right? And that one will be, thus, it will be the one having lower energy of activation in the slower step. and I'm going to emphasize it in the slow step because you need to focus on the rate determining step. So the major product is the 1 form faster. I'm going to then add here, thus we need to focus, analyze the slow step each reaction pathway. Okay, and then the one having lower energy of activation in the slow step will be the major product of the reaction. Okay, this is a really important thing. I want you guys to really understand this. It's a genetic way of presenting this idea, but you can apply this a lot. I'm gonna save this again, okay? Because you will face a lot of reactions in organic chemistry in which there are potentially different products that can be formed. And then you need to ask yourself, if I have 3 different reaction pathways, which one will be the favorite? And then quickly, as soon as you think so, you need to focus on what? On the slow step, because the slow step is the one that will determine the reaction rates. So you compare the slow steps, and the one having the lower energy of activation in the slow step, that is the favorite reaction pathway, and that is the major product of that specific reaction. Okay, that's a really important that I wanted to emphasize here. Any questions regarding this? Because it's, again, something that I want you guys to understand well. All good? Okay, so we can continue with that idea. See, here is what I said before. This is another reaction pathway. So 2 steps here is, again, step 1 is the slowest step because it has a much higher energy of activation than step 2, exothermic reaction. Now, if we look at this energy diagram, I ask the question. So the overall reaction is exothermic. We know that already. So the question is, okay, once again, how many steps in this reaction? 2 steps. Okay, so the first step, is it endo or exothermic? The first step of a reaction is endothermic, as you just said right now, if you view correctly. So it's a combination of A plus B into Z. So this is an endothermic step. And the second step is an endo or exothermic. Exothermic. So we have an example here of a reaction, and this is important too. The overall reaction is exothermic. The first step of the reaction is endothermic, and the second step of a reaction is exothermic. Okay, very important to keep in mind. And this brings me to something that a concept that is really important in chemistry, which is called the Hammond Postulate. And Hammond's postulate is really important postulate because it helps us to understand what is happening structurally in the reaction. I didn't mention, but I want to go back here to the first picture. Same 2 steps. First step is endothermic, second is exothermic. So right here, the higher energy point in a single step, we call that the transition state. Okay, transition state. That's a higher energy in a single step. It's basically the point in which the structure is more distorted from the reactants and the products, and that's why it has so much energy. Okay, so it's when the transformation is happening from AB into, for example, C here, right? So in this graph here, we have 2 transition states. One transition state is here, transition state 1, and we have a second transition state 2, over here. Okay, so which is the slowest step in this diagram, first or second? First one is the slowest step because it has a much higher energy of activation. Okay, so we have a first step here, slower step, that's the rate determining step with a transition state right here. And then a second step which happens much faster with a transition state right here. So the Hammond postulate refers to the transition states, and it's the following. For any exothermic step, the transition state is reached pretty quickly, relatively early. Because the transition state is reached quickly, there is a very high degree of similarity in the structure of the reactants and the transition state. I will expand on this idea some more. Okay. It also says on the opposite, for an endothermic step, and remember I'm talking about here steps, not reactions. For any endothermic step, the transition state is reached relatively late, and therefore the transition state resembles structurally way more the product of that step. This postulate applies equally well to transition state of one step and to multiple step reactions. Okay, so let me show you here. First of all, why do we care about the Hammond postulate? Well, because the information about the structure of a transition state is really important to understand reactions mechanisms and actually to make predictions about reaction rates, competing reactions, final products. Okay, we will apply that, as I said, a lot in organic chemistry next semester. So here is an example of a single step reaction. In this single step reaction, we have the reactants here and the products here. Okay, transition state is right here. So as you can see on this, I'm going to rephrase now the Hammond postulate in a way that is a lot easier for you to understand. The energy of the transition state is closer to the energy of the reactant, is much farther from the energy of the product. Okay, because the energy of the reactant and the energy of the transition state, they are so close, that actually tells you that the structure of the transition state resembles the structure of the reactants. Okay, so that's what that is telling you. So for any, and this is, obviously this is an exothermic step. So in any exothermic step, you will have an early transition state. And in early transition state, the structure of the reactants resemble the structure of the transition state. So what that means is, and what's the connection with that with reactions mechanism? Okay, so I'm gonna write it over here, and this is the key. So if the transition state and the reactants are structurally similar, which is the case in an early transition state, any factor stabilizing the reactant will also stabilize the transition state. On the opposite, if the transition state and the reactants are structurally similar, so if we have an early transition state, any factor stabilizing the product will not have a major impact on its stability of the transition state. So, repeating this idea, any exothermic step will have an early transition state because the energy of the transition state and the reactants, they are closer to one another. An early transition state actually means that the structure of the transition state is similar to the structure of the reactants. Because of this, any factor that stabilizes the reactant will also stabilize the transition state. So if there is an stabilization of the transition state, then the stabilizing means lowering energy, and lowering the transition state in energy will mean lower energy of activation, faster reaction. Okay. On the opposite, if the transition state is early, factors making the product more stable, product of that step, will not impact a lot the stability of the transition state because structurally they are not that similar. Okay. So the summary of this is that in an early transition state, if you introduce a factor that stabilizes the reactant, the reaction will go faster because the transition state will also be stabilized. And on the other hand, in an exothermic step reaction, if you introduce a factor that stabilizes the product, the reaction rate will not change because they are structurally different. This is a really important thing, okay? Now repeat it and then write it over here because I want you guys to really keep this in mind, okay? So once again, factors, all right? If there is any question, you guys feel free to ask, okay? So I'm gonna say now, as a summary of this, that for an early transition state, okay, in early transition state, factor stabilizing the reactant will make the reaction faster, okay? Because it's early, because the transition state and reactant are structurally similar. And on the other hand, the factor stabilizing the product will not make the reaction faster because they are structurally similar. The transition state and the product are not structurally similar, okay? And that is a really important thing because that will impact a lot how you can manipulate reactions in the future to favor a product or vice versa, okay? So the transition state, somebody's asking me what is the transition state exactly. The transition state is right here. So if you're thinking about A and B becoming into C, okay? So the transition state, basically you have two molecules forming one, right? There is a bond that is being formed between A and B to create molecule C. So the transition state is a point higher in energy in this pathway in which the molecules are coming, the atoms are coming close together to form the bonding, and the energy at that point is the highest in the process. That's what the transition state is. The transition state is a point with a higher energy in a single step. Okay, so once again, if you're transforming A and B into a product, the higher energy point of this pathway, that's the transition state. Okay? Any other question? Or is that clear, Rachel? So what's the question exactly? Repeat again, and I'll repeat as many times as needed.
So it doesn't like symbolize going from increasing energy to decreasing energy. It's rather like A and B and are adding to C and
Okay,
whatnot.
so okay, don't go. So we have this is a reaction pathway, right? A and B are forming C and D. Okay, you can see that, right? Yes. Now, in order for A and B to get into C and D, there is a first step in which an intermediate is formed. Let's call this C. So the reaction first goes through A and B transforming into C, and then C is being transformed into C and D. I mean, we can call this whatever you want, okay? Here is another picture. Okay, so here is another example. A and B is transforming to C, and then C is being transformed into D and E. It's clear here, okay? So what is a transition state? Well, in this reaction, there are two steps, step 1 and step 2. So the transition state is the point of higher energy in a single step. So when A and B are coming together to form C, there will be a point of higher energy in this transformation because the structure will be distorted in between these two until it goes to C. Then the atoms will rearrange. I'm going to give you a more clear example. Okay, let's say you have a carbon in A, okay, that is sp2 hybridized. What is the optimal angle of an sp2 hybrid carbon? What is the geometry of an sp2 hybridized carbon? Anybody knows? 120 degrees, right? So if we are analyzing a reaction in which we are going from an sp2 hybridized carbon, let's say, to an sp3, what is the optimal angle of sp3? 109.5. So we are going from a carbon that is 120 degrees with 3 bonds to another carbon that is going to be in the new product, 109.5 4 bonds. In this transition in which a carbon is changing the hybridization, there will be a point in which the angle will be highly distorted until it can be rearranged to form the 109.5. That is a transition state. Okay? Just to give an example. You will see this more no, there is no more names for the transition state. Transition state, that's it. That's it. The correct way to say it. Okay. So let me rephrase this here. Hammond postulate. Okay. Once again, in any exothermic step, the transition state is early. It means that it's reached pretty quickly because so the higher energy point is reached pretty quickly. That actually means that in that higher energy point, the structure of that intermediate resembles more the reactants than the products. So it's structurally more similar to the reactants than to the products. Because remember, this is a transformation between reactants and products. So whatever the structure here is going to be converted in a structure here. So at the higher energy point, that structure is closer to the structure of a reactant. Because of that, so and that's an early transition state. Because of that, any factor that stabilizes the transition state, or vice versa, any factor stabilizing the reactant will also stabilize the transition state. If the transition state is stabilized, it will have lower energy. The energy of activation will be smaller as a reaction. On the opposite, any factor stabilizing the product, because the product structurally is not that similar to the transition state, anything making this more stable will not make this more stable because the structures are not alike. So any factor stabilizing the product will not make a difference in terms of reaction rates. Okay, let me now give you another example. So this is the opposite reasoning. So here we have single step. So is this step endo or exothermic? Step on the picture. It's an endothermic step. Okay, so it's an endothermic step. Therefore, in this endothermic step, as you can see, the transition state is right here. It is the highest energy point. And this transition state is closer in energy to the product of that step. Is farther from the reactants. So I answered that. I was asked a question. I will address a question in 5 minutes. Let me finish this idea, okay? So once again, here is a reaction pathway. This is a single step reaction. In this single step reaction, okay, it's an endothermic step. Therefore, the energy of the reactant is closer to the energy of the product. So this is what we call a late transition state. A late transition state actually means that the structure of the product is actually resembles the structure of the transition state. So if the transition state and the product of that step are structurally similar, and that's a late transition state, any factor stabilizing the product will also stabilize the transition state. Once again, endothermic transition state here, closer to the product in energy, meaning that these two are similar in terms of a structure, structurally similar. If they're structurally similar, any factor stabilizing the product will also stabilize the transition state. And vice versa, if the transition state and the reactant are not structurally similar, which is a case for the late transition state. So here we have the reactant here, the transition state here, they're far away in terms of energy, they are not alike, okay? So any factor stabilizing the reactant will not have a major impact on the state of the transition state. Summary, so exothermic steps, right? Early transition state, structurally similar to a reactant, endothermic step, late transition state, the structure similar to the product. And then I can finally make the same analogy. Then I will address a question. For a late transition state, a factor stabilizing the product will make the reaction faster. It's a late transition state because transition state and product are structurally similar. A factor stabilizing the reactant will not make the reaction faster because transition state and reactant are not structurally similar. Okay? That's what the Hammond Postulate says. So somebody's asking me what is a factor that actually can stabilize the reactant? Is a chemical or it could be something about the reaction. We'll get deeper into this in orgochem, but I'm going to give you an example. Okay? The solvent can solvate better a reactant or the product depending on the structure of this. So if you have a solvent that solvate better the reactants, that will make the reactant more stable. If you have a solvent that solvates better the product, that will make it more stable. Depending on which reaction pathway you have, you might want to pick a solvent that will make your reaction faster. Does that make sense? Okay, my pleasure. All right, so that's an important thing. Okay, so any other questions? So what I want you guys to know from this thermodynamic summary of the reaction is basically to be able to recognize uh, multiple steps reactions, endo and exothermic reactions, endo and exothermic steps, and then the Hammond postulate, what it is, and how you can use it to make a prediction in a reaction. In genetic terms, we are not talking about a specific reaction. We will do that in organic chemistry in the next semester.